Okay, so in this lecture, we start with the concept of eigenvalues and eigenvectors. Eigenvalues and eigenvectors. And we will have a series on lectures which will help us characterize the concept of diagonalization of a linear operator. Okay, so in very literal sense, a linear operator is said to be diagonalizable if there exists a basis with respect to which the matrix representation of the linear operator is a diagonal matrix. Okay, so let me just start with the simple definition of what diagonalization is. So let V be a finite dimensional vector space over a field F. Okay, so now we obviously know that provided a vector space, if it is finite dimensional, then there obviously we can associate a matrix to an arbitrary linear operator defined on this vector space, right? So let V be a finite dimensional vector space over a field F. Let T be a linear operator defined on V. That is, so T is basically a linear transformation from V to V, right? That is, T from V to V is a linear transformation. Is a linear transformation. Okay. T is said to be diagonalizable if there exists an ordered basis B of V such that the matrix representation of T with respect to this ordered basis is a diagonal matrix. Clear? Some other way of viewing this is that provided uh, a linear operator T on a finite dimensional vector space V over F, we can think of it like, say, suppose the matrix representation of T with respect to some ordered basis BV is A, okay, where BV is some ordered basis of V. Now we know that if we have a matrix representation of some linear operator with respect to some ordered basis, then if we change the basis, then the matrix associated with the new basis must be similar to this given matrix. Okay, where B is an ordered basis. Then the matrix A, we can define it now for the matrix A. That is because this is pretty obvious, because since you have a 1-1 correspondence between the structure of a linear operator and a matrix, and in this case it must be a n cross n matrix provided the dimension of the vector space is n. Then you can give an analogous definition for a matrix as well. So then A is said to be diagonalizable if A is similar to a diagonal matrix. And the equivalence of this definition, it solely relies on the fact that, suppose now if we consider the first definition, okay, so that means that there exists some ordered basis, say B. So if you find the matrix associated with this basis B of the linear transformation, then this should be a diagonal matrix, right? You know A is the matrix representation of that same linear operator with respect to some other basis, PV, some other ordered basis. And we know that in such case, the matrix representation of a single linear transformation with respect to two different bases are similar, right? So it's of the form like this, right? So that means A is similar to this diagonal matrix. Okay, that is the form of viewing it. Okay, so yeah, so two matrices had to be similar if there exists an invertible matrix, for example P, such that A can be written as A and B can be written in this form. So two matrices A and B are said to be similar. Now, obviously, I am not talking about the dimension of the matrices, because since we are considering a finite dimensional vector space and we solely focus on a linear operator, so the matrices associated with whatever we study in this lecture are all square matrices, right? So they are eventually square matrices. That's why I'm not talking about the dimension of the matrices. And since whatever matrices we work with, for example, here we have A and B, the background of these matrices are basically representations of linear transformations, linear operators rather, right? So they both of them will have the typically they will have the same dimension, right? So that's why I'm not specifically talking about dimensions. So two matrices A and B are said to be similar if there exists a invertible matrix P, which we also have a dimension corresponding to matrix multiplication, right? Such that A can be written as P inverse B. Clear? So then two matrices are said to be similar. That is the very basic definition. So our main target of whatever lectures we will have, including this one, is to characterize the concept of a diagonal matrix and to just, kind of construct certain conditions which help us judge whether a provided linear operator is diagonalizable or not. That's the main goal of this series of lectures. Okay. Diagonal matrices are obviously pretty important because they are very simple. They are very simple to use. They are very simple in nature. They are, they are very easy to operate in any field. They help us view the structure of the linear operator very simply, and obviously they have very highly, visualizable geometrical importance. Because matrices, the main use of matrices is some sort of rotating and scaling of vectors. Okay. I obviously can't cope up with with visualizing what matrices do to vectors in this lecture, obviously. But typically speaking, matrix multiplication on vectors, they actually rotate or scale vectors on the plane you draw them. So the importance of diagonal matrices are they just scale the vectors, and analyzing vectors which are just scaled is much easier than when rotated. That is the very typical thing. Okay, the geometrical importance of a diagonal matrix. Okay, and in a mathematical point of view, diagonal matrices are pretty simple to use. Okay, so let's come up to the first important definition of starting this series. That is the concept of an eigenvalue. Okay, so let T be a linear operator on a vector space V over a field F. Let C be a scalar, that is an element of F. C is said to be an eigenvalue of T if there exists a non-zero vector alpha such that T of alpha is equal to C times alpha. Okay, this is the condition. Yeah, I often denote T of alpha as T subscript alpha. Okay, so in that case, we say C is an eigenvalue of T, and in that case, alpha is said to be the eigenvector associated with the linear operator T corresponding to the eigenvalue C. Corresponding to the eigenvalue C. Clear? Okay. Or in some books, you just simply get the definition that eigenvector associated with the eigenvalue C. That will also do. That is, if you have only this set of words, yeah. Associated with the eigenvalue C. This will also do. Now, obviously, you can notice that I have not used the concept of a finite dimensional vector space because this definition actually doesn't need the concept of a finite dimensional vector space, right? Now, if it is a finite dimensional vector space, then we obviously get square matrices, square finite dimensional matrices, and then on an analogous point of view, we can obviously define an eigenvalue for a matrix as well. So let me just define it here. Definition: let A be a n cross n matrix over a field F. C in F is said to be an eigenvalue of A if there exists a non-zero column vector 0 not equal to alpha being a non-zero column vector. So if it's n cross 1, fn cross 1, such that A times alpha here is equals to C times alpha. Okay. So this is the exact thing which we were talking about actually, that if you multiply a matrix with an eigenvector, because alpha is again so alpha is typically the eigenvector associated with the eigenvalue C. So if you have a matrix multiplication of an eigenvector which is associated with some eigenvalue C, then the vector just gets scaled. It doesn't get rotated on a geometrical point of view. Okay. So in that case, alpha is said to be the eigenvector associated with the eigenvalue C. Clear? Okay. Now, obviously, if T is a linear operator on a finite dimensional vector space, so this is just a simple observation that if T is a linear operator and V is finite dimensional, then T of alpha is equals to C alpha is equivalent to saying A times alpha is equals to C alpha for some matrix A, or suppose say V is finite dimensional with dimension n, then for some n cross n matrix, right? Because obviously you can form an n cross n matrix using some basis of V, and conversely if you have a matrix, then you can define a linear operator with respect to that matrix. We know, right, that LA of x given as AX, where x comes from a vector space of dimension n, which is isomorphic to Fn cross 1, gives you a linear operator, right? I have a detailed lecture on these sort of things. I'll give that in the I button. Okay. So, okay. Now this is pretty obvious to notice that, or rather I should say about this as a question, that we have an analogous definition for a matrix, right? So my question is that if I consider the matrix as a matrix representation of the linear operator on the finite dimensional vector space V with respect to some ordered basis, then is there a change in the eigenvalues if the basis is changed? Okay. So to answer that question, we first need to analyze the concept of an eigenvalue more. Observe that if T is a linear operator. So we are speaking about finite dimensional vector space from now on. Okay. So if T is a linear operator on a finite dimensional vector space V, and if C is an eigenvalue of T, then we know that T minus Ci, or rather I should just simply use the statement that T of alpha is C alpha for some non-zero vector alpha in V, right? But this can be written as T minus Ci of alpha equal to 0, because I is the identity mapping, identity linear operator. So I of alpha will be just alpha, and T of alpha is T alpha, right? It equals to 0. Now let A be some matrix representation of T. Then, then 1 is equivalent to writing A minus Ci times alpha is equals to 0, where I is here the I is the n cross n identity matrix. Okay. So we are using the dimension n cross n, so you can just assume that the vector space has dimension. Okay. Okay, clear? Now obviously alpha is non-zero, right? There exists some alpha which is non-zero. Recall that if you have a system of linear equations of this form, then there are two sorts of equations, right? So two sorts of solutions of this column vector x, right? So one is the trivial solution. The trivial solution is basically x equals to 0. And there are non-trivial solutions. Non-trivial solutions are when the values of x are non-zero. Obviously, x equal to 0 is an obvious solution to this equation, but there exists non-zero solutions as well. Okay. And a system of linear equation has a non-trivial solution when the determinant of A is 0, or determinant of the matrix associated with this system of linear equations is 0. So we can use this concept here. Now since alpha is non-zero, therefore this system has non-trivial solution. So that means determinant of A minus Ci is equals to 0. And obviously notice that these steps are all equivalent, because if you consider some C in the underlying field F, then A minus Ci, the determinant of this equal to 0, implies A minus Ci times some alpha equal to 0 has a non-zero solution, or has a non-trivial solution. But that means there exists a non-zero alpha such that A times alpha is equal to C alpha. But that implies C is an eigenvalue. So since this set of statements are equivalent, we can characterize the concept of an eigenvalue as root of this equation, because this is a polynomial equation, right? Therefore, provided a matrix A, C is an eigenvalue of A if and only if the determinant of, or rather I can think of it as if and only if C is a root of the equation determinant of A minus xi equal to 0, right? A minus xi is obviously a polynomial equation from the concept of determinants. One more thing, this is pretty important to observe, that if A is a matrix over a field F, then C belongs to that same field F only, right? So thus this is now easy to find the eigenvalues if you are given a matrix, because what you actually need to do, you need to find this polynomial and you just need to find the roots of it. For example, let us consider an example. Let A be an n cross n matrix, or rather let's say A is a 2 cross 2 matrix, over the field C, such that A is defined as the following matrix. So it's 0, 0, minus 1, 1. Okay. Then what is A minus Ci, or A minus Xi I should use? So this is determinant of minus x minus 1, 1 minus x. So that's simply x squared plus 1, right? Therefore, A minus Xi, so A minus Xi equals to 0 implies x squared plus 1 equals to 0, and then the roots of this are x is equals to plus minus I, right? Right? Now this is an obvious eigenvalue of A because the underlying field is complex, right? Therefore, the eigenvalues of A are I and minus I. Now observe one more fact. Suppose I had chosen the underlying field to be R. Sorry. Yeah, okay. So suppose I have chosen the underlying field to be R. Then you can obviously solve this equation to get these roots, but X no more belongs to R. But we need the eigenvalue to be inside the underlying field. So in this case, A has no eigenvalues. A has no eigenvalues. Clear? In this case, A has no eigenvalues. Okay, so from here also, we get one important observation and one important question arises. So the observation, let me just write it down. The observation is as, if the matrix is defined on C, or the linear operator is defined on a finite dimensional vector space, because since we are talking about matrices, we need the linear operator defined on a finite dimensional vector space, over C, then the matrix or the linear operator always has an eigenvalue. And the reason is that these eigenvalues are roots of some polynomial, right? These eigenvalues are roots of some polynomial. Now we know that any polynomial has a root in the complexes. The complex number system is algebraically closed, right? It's algebraically closed. So any polynomial you choose, it will always have roots in the complexes. Therefore, the polynomial whose roots are the eigenvalues, they will always exist if the underlying field is the complexes. Therefore, if you define a finite dimensional vector space over the complex field, or the matrix takes its entries from a complex field, then the polynomial equation A minus Xi will always have a root, right? So that is the reason why the matrix or the linear operator will always have an eigenvalue, right? But if you choose the underlying field to be R, then we know that there are certain polynomials which doesn't have a root in R. For example, here we had x squared plus 1. There's no root in R. So in that case, eigenvalues may not exist. But over C, it will always exist because C is algebraically closed. I hope this observation is pretty clear. The next observation is, or rather I should say the next question is or rather I should say, are eigenvalues there for any linear operator defined over a vector space? Okay. Now there is one very typical answer which we had just observed previously, that if the underlying field is not algebraically closed, that is, the underlying field is such that if a polynomial may not have a root in it, then eigenvalues may not exist. So if V is a finite dimensional vector space over, so we are talking about finite dimensional vector space because the concept of determinant relies on the fact of the matrices, right? So we need a finite dimensional vector space to have the concept of a matrix, hence the concept of a determinant. So if V is a finite dimensional vector space over a field K, where K is not algebraically closed, where K is not algebraically closed, then a linear operator on V may not have eigenvalues, right? And the example is what we just gave you, right? Okay. Obviously, notice that if the matrix was given in this form, if it was in this form 0, 1, 1, 0, then the determinant, then this polynomial would have come of this sort, right? It's x square minus 1. This obviously has roots because the roots are 1 and 1. These obviously belong to R. So if the matrix was defined like this, then this equation has roots 1 and 1 which are in R. So in that case, this matrix has an eigenvalue, or the linear operator defined with respect to this matrix has an eigenvalue, right? So in case of a finite dimensional vector space, it obviously depends on the underlying field. But what happens if the vector space is not finite dimension? So in that case, eigenvalues may or may not exist again. Okay, so there is not a general overview that eigenvalues will exist for any any linear operator over a vector space. Now, we had discussed now about finite dimensional vector spaces. Let us consider what happens if you have an infinite dimensional vector space. Okay. Okay. So consider this example. So let T from V to V be a linear operator where V is the space of all continuous functions, continuous real valued functions defined on R by the following. So T of f is the integral 0 to x ft dt. So Tf of x, right? That is basically T of f of x. That is what we are talking about. So it's in this form, it's clear. Okay. So it's obviously a vector space over R, right? It's very easy to understand. Now suppose this linear operator has an eigenvalue. Okay. So suppose T has an eigenvalue. Suppose T has an eigenvalue, say C. Say C. Then there exists a non-zero function f belonging to V such that Tf of x is equals to C times fx, right? But Tf of x is integration 0 to x ft dt equals to C times fx. So we can differentiate on both sides, right? So we can differentiate on both sides. So differentiating on both sides, we get fx equals to C times df by dx. This is what we get. So now we can obviously find a solution to this because this is a very easy differential equation, right? So observe that the solution to this differential equation is of the form a times e to the power minus 1 by cx, right? Sorry. Yeah. Okay, let us solve this. Let us solve this here. That will make it easier. Okay. So solving this is just let fx equal to y. Suppose this is 1. Therefore 1 implies c times dy by dx equals to y. That implies dy over y is equals to dx over c, right? So if you integrate both sides, we get ln y is equals to x by c plus some constant c1, but that implies y is equals to, you just raise both sides to the power of e, so this becomes e to the power x by c times e to the power c1, but that's again a constant. So this is of the form a times e to the power x by c, and you can consider this to be fx. Clear? Clear? Now what is f of 0? What is f of 0? So f of 0 is a, right? Now, since you have this equation that f of x is equals to lambda times df by dx, this equation says that f of 0 is nothing but 0, because this becomes 0 when you put x equals to 0, right? So f of 0 is equals to 0. So this equation and this equation means f of a must be equal to 0, but a equal to 0 means f is completely 0, f is identically 0, but that's a contradiction, right? But that is a contradiction because we had assumed that f is an eigenvector associated with the eigenvalue c, and eigenvectors are non-zero by definition, right? That is a contradiction, as f was assumed to be non-zero, right? Therefore, this linear operator has no eigenvalue, right? So that's an example which will which just states the fact that every linear operator doesn't need to have an eigenvalue. And this example also states the fact that infinite dimensional vector space are a bit less important than finite dimensional vector space, because we can talk a lot about finite dimensional vector spaces, right? The only difference in case of a finite dimensional vector space makes in between the existence of an eigenvalue and existence of an and no existence of an eigenvalue is simply the underlying field. That's it, right? So basically what happens is that eigenvalue exists for every linear operator in a finite dimensional vector space. It just depends on the underlying field. If the underlying field is not algebraically closed, then we cannot say that it exists. But they exist as roots. They do exist as roots, because if they're roots of polynomial, the roots obviously exist, but we cannot conclude the fact that they exist as eigenvalues because they do not belong to the underlying field. That is the only thing we have in the finite dimensional case. Okay. So let us just end this lecture with two important observations, or you can say as definitions, you might say, which are the concepts of a characteristic polynomial. Okay. So let A be a n cross n matrix. Suppose we mention the field over the field f. Over the field f, then the polynomial determinant of a minus xi, where x is an unknown, denoted as, we will denote it as fa of x, is called the characteristic polynomial, of the matrix A. Observe that the degree of the characteristic polynomial is the dimension of A, right? It's the dimension. Also observe that the characteristic polynomial is a monic polynomial. Right? Because whatever multiplication you have in the case of this determinant, the coefficient of x always remains 1 or minus 1, right? So the highest power of x is associated with this x value only, right? If I give you a simple example for this observation, if you consider a matrix, let's say, 1 minus x, 2, 3, 2 minus x, then the determinant is of the form 1 minus x into 2 minus x minus 6. So the coefficient of x in both the cases are only 1 or minus 1, right? So it becomes x squared, right? So the highest degree attained by this polynomial is associated with the x is having coefficient of 1 or minus 1. That is the only thing I was speaking about, right? So it becomes x squared plus 2 minus 3x minus 6. Yeah, clear? Okay. So obviously observe one more thing, that eigenvalues are basically roots of characteristic polynomials. So eigenvalues of a matrix A is the root of the characteristic polynomial of A. Clear? Now we had started off with a question that if we change the basis of a linear operator, then will the eigenvalues change? Okay, we claim it does not change. That is the so you can have this concept as a proposition. That eigenvalues of a linear operator defined on a finite dimensional vector space V over F does not change with change in basis. I should give it a more clarification. Eigenvalues of a matrix let me frame it like this: for matrix associated with a linear operator defined on a finite dimensional vector space V over F does not change with the change in basis here. Right? It's clear, right? So what I mean to say is that if you have a linear operator T defined on V, where V is finite dimensional, then if you have two ordered bases, so you have B and B1 are two ordered bases of V, then the matrix of T with respect to B and the matrix of T with respect to B1 will have same eigenvalues. Now we have already spoken of the fact that eigenvalues are nothing but roots of the characteristic polynomial. So if we just show that two matrices which are representations of a linear operator with respect to two different bases have the same characteristic polynomial, then it suffices to show that, or it suffices to prove that they will have same eigenvalues. That is, if A is equals to the matrix representation of T with respect to B, and let this be considered as B1 and B2, and let B be the matrix representation of T with respect to B2. If we show that the characteristic polynomial of A is same as the characteristic polynomial of B, then it suffices, right? Suffices to show that they are having the same eigenvalues, right? But also we know the fact that two matrices which are individually representation of a linear operator with respect to different bases, they are similar, right? So obviously, therefore, since A and B are similar, being matrix representations of a linear operator with respect to different bases, therefore it suffices to show that similar matrices have same characteristic polynomial, right? So we'll simply show that. Now observe that, so if A and B are similar, then there exists invertible matrix P such that A is equals to P inverse B. So that implies what is A minus xi. So it simply can be written as P inverse BP minus xi, and I can be written as P inverse P, right? Okay. So this implies A minus xi can be written as, so we can take P inverse common outside. As x is simply a scalar or an unknown, right? So it will obviously commute, right? In some, so it's a column vector, right? So we can obviously assume P inverse to come outside. So if I choose P inverse outside, then I simply have this to be as B BP minus XP, right? Right? Clear? See, the value x is obviously in the field because the roots of x are the eigenvalues. So x is in the field. So obviously it is a constant. I think I said it's a vector, so I'm very sorry about that. It's a scalar. It's a constant from the field. So it will obviously commute with the polynomial. So it's BP minus XP, right? Then if we take the P from the right, then it will become P inverse of B minus XI P, right? Now simply take determinant. The determinant of A minus Xi is equal to determinant of P inverse of B minus Xi times P. But that is, now we know determinant distributes. So this is this times P. But these are all real values, right? These are real values. So they will obviously commute. So P inverse, the determinant of P inverse will commute with this, and then it will associate with P inverse P. That is, we can write it as this times this, but that is equal to B minus Xi times determinant of I, which is 1. So that is nothing but B minus Xi. So that implies the characteristic polynomial of A equals the characteristic polynomial of, right? And that implies A and B have the same eigenvalue. So we have basically stated the fact that similar matrices have similar eigenvalues. Okay, that is the thing. Yeah. So the next important observation which we want to talk about is that observe that if alpha is an eigenvector associated with eigenvalue C, then A minus Ci, or rather I say it as T minus Ci of alpha is equals to 0, right? For a linear operator T, right? Or I should use for the linear operator. But notice that if T is a linear operator and I is also a linear operator, right? It's a trivial linear identity linear operator, then T minus Ci for some scalar C is also a linear operator, right? So that means alpha is in the null space of this linear operator T minus Ci, right? It's in the null space of the linear operator T minus Ci, right? Is it clear? Now let W be the collection of all eigenvectors of T associated with C. Okay. Then W is called the eigenspace of the vector space V associated, because W is obviously a subset of V, right? Because these eigenvectors are elements from V. So it's called an eigenspace of V associated with the linear operator, associated with the eigenvalue C. Is it clear? Now W is typically a vector space. That's quite trivial to notice that W is a vector space. W is a vector space over the same field. Okay, or I should say W is a subspace of V over the so W is a subspace of V. You can choose take this as an exercise. Okay, clear? We tend to prove that this subspace is same as the null space of T minus Ci. That is, they are same. Okay, and that is quite easy to prove because suppose we take an element alpha from W, then that implies T minus Ci times alpha equals to 0 by definition, since alpha is an eigenvector associated with the C. So this implies T of alpha is equals to C alpha, but that implies T minus Ci of alpha equals to 0. So that implies alpha belongs to the null space of T minus Ci. That's quite trivial. So that basically means W is contained in the null space of T minus Ci. Conversely, if alpha is in null space of T minus Ci, then that means T minus Ci of alpha equals to 0, but that means T alpha is equals to C alpha, which means alpha is in the space W, right? Therefore, W is equal to the null space of T minus C. That implies dimension of an eigenspace is the nullity of the space of the linear operator T minus Ci. Okay? So that's another important observation for today. Okay. So yeah, so we end this lecture today. In the next lecture, we will be coming up with more important characteristics of eigenvalues and eigenvectors associated with linear operators and matrices. So meet you guys in the next lecture.